Now in this video lecture we would be deriving similar relation that we derived for variable batch reactor in the previous lecture. We would be deriving here relation for variable volume of flow reactors, right? So here flow reactor with variable volume, right? Now to get a similar expression for variable volume flow reactor, we need, since it's variable volume, so same as before, we would be deriving relation of volume in terms of conversion x, right? Then from the expression of volume in terms of conversion, we would be finding expression for concentration. That concentration would be substituted in rate law expression, right? So similar procedure we would be following, right? And to get concentration of gaseous phase reactions, we can use the gas law equation, right, to find the concentration of gaseous reactions, right? So the concentration, if suppose we have this is a variable volume, say it's like this, it has a different shape, it is variable volume, right? So at any point, at any time t, right, at any time t, right, concentration at any time t would be, concentration we know is moles per liter. So here moles would be molar flow rate, right? So concentration would be molar flow rate divided by volumetric flow rate. Volumetric flow rate. This would be F at any time t, Ft upon nu t, right? Nu t denotes volumetric flow rate, Ft denotes molar flow rate, right? And if you want the same expression, the expression for concentration of gas phase reaction can be obtained from gas law equation, and gas law equation is your PV is equals to Z nRT, right? And concentration is moles per unit volume, so it would be N upon V, right, P upon ZRT, right? So this would be concentration P upon ZRT, right? So these two equations, right, concentration, right, using this formula at any point t, and concentration of gas phase reaction can be taken from gas law equation. So these two equations can be equated, right? Ft upon nu t and divide is equals to P upon ZRT. This is volumetric flow rate. So these two equations, equation 1 and equation 2, can be equated. You get Ft upon nu is equals to P upon ZRT, right? Equals to ZRT. Now for this equation is for at any time t inside the reactor, right? Now the same equation when the reactants are entering the reactor, right, at the entrance point, right? The same equation for the entrance point would be, this would be Ft0, right? Ft0 represents the total moles, right? This, it represents the total moles divided by nu 0, volumetric flow rate at the initial point, at the entry point, right? This would be equal to nu 0, right? Sorry, P0 pressure T0, right? This is at T is equals to 0. Or at entrance point, right? Now these two are the equations. We would be dividing these equations, right? Or we'll take the ratio of the equation, right? We'll take ratio of this to this. Let's call it as third, call it as fourth, right? So we would be taking ratio of third to fourth, right? If you divide these two, this will come out to be nu is equals to nu 0, right? If you divide it, you will get nu is equals to nu 0 ft upon ft0. If you divide these two, right, you get ft upon ft0, right, is equals to p0 upon p, sorry, ft upon ft0. Then you have this p0 upon p, right? Then you have t upon t0. Right? Now you got this expression for volumetric flow rate, right? Volumetric flow rate, this is at any point at any time t, and this is the initial volumetric flow rate, right? So using these two, you can have, this is the relationship between initial and at any point at time t volumetric flow rate, right? We would be using this expression in a while. Right, now we know we can now express concentration, right, since it's a flow system. So we would be expressing concentration of species J in terms of flow rate, right? Concentration we know is flow rate upon Fj is equals to nu, right? And expression for Fj will remain as it, nu will come from this. It would be Fj upon nu 0, Ft upon Ft0 upon P, T upon T0. Right, so this will solve out to be Ft0 upon, this will go up, it would be, this will solve out to be Ft0 upon nu 0, right? Then P upon P0, T0 upon T, right? And Fj upon this Ft, you have Fj upon Ft, P upon P0, T0 upon T, right? This is, if you take all these above, this is what you will get, right? So this is your CT0, this is your initial total number of moles, these total number of volumetric flow rate, I'm sorry, this is the total molar flow rate. Ft0 is total molar flow rate, this is your initial molar flow rate, this is your initial volumetric flow rate, and this is your flow rate at any time t, right, for any species J, right? So this will come out to be CT0, this is your CT0, this is initial, so this is what, if you look at this equation, Ft upon nu is molar flow rate upon volumetric flow rate is your concentration, right? So we will replace it with CT0, right, and Fj upon Ft and P upon P0, this you will write down as it is, Fj upon Ft, P upon P0, T0 upon T. Right, concentration of any species J, right? This is how you will relate it. Now we need to express concentration in terms of conversion, right? We need to express concentration in terms of conversion. This is what we want, concentration in terms of conversion, and for this we need volume first in terms of conversion, right? Once you have volume in terms of conversion, you can get concentration in terms of conversion, because we know that concentration is molar flow rate divided by volumetric flow rate for a flow system, right? So to get relationship between molar flow rate, right, and your conversion, molar flow rate, or I'm sorry, for volumetric flow rate and conversion, we would be using this equation, right, that we get from stoichiometric table, like we did before, right? Like I said, that in order to build any relationship, to build any relation between rate law and conversion, we would be needing rate law, right? Rate law equation is the same one that we use, R is equals to K Ca Cb, right, product of concentration, and we need stoichiometric table as well. This is what we have studied in the previous lectures, right? So now we would be using this relation from the stoichiometric table, right, that relates flow rate at any time t to the initial flow rate, right? And we have this the flow rate at any time t, right, is related to conversion x as per this relation, right? So this is your molar flow rate. Molar flow rate is related to conversion x as per this equation. We will now further solve this equation like we did for batch reactors, right? So now first we will substitute this expression for Ft here in this equation, right? So nu is equals to, we'll substitute it in volumetric flow rate, right? We'll substitute this molar flow rate Ft, we'll substitute this in this expression, and this will come out to be nu is equals to nu 0. In place of Ft we will substitute it from here, because we need relation between nu here, this is not mu but nu, volumetric flow rate in terms of conversion x, right? So if you look at this is volumetric flow rate. To get expression for conversion x here, you will put, or you will express Ft in terms of x using this equation, right? So it would be Ft0 nu is equals to, this is nu 0. In place of Ft, you will substitute it from stoichiometric table. It will come out to be Ft0 plus del Fa0 dot x, right, divided by Ft0, P0 upon P, T upon T0. Right? This is, if you solve this 1, then you have del Fa0 upon Ft0 dot x, right? Now, like we did before in batch reactors, what is this? This will represent this part. This represents your moles of A, right? Moles of A passing through at any point, right? Out of the total moles. Ft0 represents total molar flow rate. Fa0 represents molar flow rate of reactant A, of species A, right? So this represents your mole fraction, right? This is your mole fraction of A, right? As per the definition of mole fraction is number of moles of A passing through at any point out of the total moles. This is total moles passing at any point, right, at time t. Out of the total moles passing, Fa0 is that of species A, right? So which is your, as per the definition, the mole fraction of A passing through at any time t, passing through a point at any time t, right? So we will express this as, like we did before, del y0, right? Or I'm sorry, it was y0. So this is your p0 upon p t upon t0. This is your nu 0 1 plus del y0 x p upon right. This is how it looks like. Now this is your, this would be your epsilon, right, like we did before. So do watch the previous lecture before you watch this, right? 1 plus this del y0. Y0 is your, for, this is for species A, right? So this would be replaced by epsilon x, p0 upon p t upon t0, right? So here epsilon is del y0, right? And what does del represents? Del represents this part, right? And y0 is your mole fraction of Fa0, right? This is what it represents. Now we will come to this part, right? And the concentration of species J, like concentration of any species J would be Fj divided by nu, right? Molar flow rate divided by volumetric flow rate. And molar flow rate of species, if you just look at this, molar flow rate of any species is seen from this from the fourth column, right? So molar flow rate would be, F for any species J would be Fj is equals to Fa0 theta j minus b upon Ax, right? Molar, this is molar flow rate for any species J. I'm sorry, it would be, if you look at this, this would be nu, plus, this is the generic form, theta j plus nu j x. For any species J, it would be taken from here, right? So this is your volumetric flow rate. What does this represent? C upon A. This is moles of species J, moles of species D, right? Similarly, moles of species A, right? Now we would be using these two expressions, and we will substitute this in here, right? Fj would be taken from this equation and nu would be taken from the below expression that we have just derived, this one, right? So here the concentration will come out to be, it would be Fj, which would be Fa0 1 plus epsilon x p0 upon p T upon T0, right? This is how we will get the expression for concentration, right, which we will substitute in rate law, because we need expression for concentration to express rate in terms of concentration. To express rate in terms of conversion, we need expression for concentration in terms of conversion. So once we have conversion in terms of concentration, we can substitute this in rate law equation, CACB, right? And this is what we are trying to achieve here. Cj would be now, if you solve this further, you will get right. So you will solve this to be, this would be FA0 right. This would be Ca is equals to, this is molar flow rate, this is volumetric flow rate. Molar flow rate divided by volumetric flow rate will become Ca0. This is initial concentration, right? Then you have this expression, right? Then you get P upon, you bring this up, you get P upon P0, T0 divided by T 1 plus epsilon x, right? This expression relates your concentration to conversion x, right? So from here you get relation between concentration and conversion x. So you will substitute this concentration for different species, right, based on this expression in the rate law equation to get rate law in terms of conversion x, right? So I hope this is clear, right? Just to revise quickly, let's just see it. To express volumetric flow rate, right? We have done this for a flow reactor that has variable volume, right? So since it's variable volume, so we need expression for volume in terms of conversion x, right? So we will begin by using the concentration for any gas phase reaction can be taken from gas law equation, right? And from the simple formula, concentration is molar flow rate divided by volumetric flow rate at any point at any time t, right? So this is the initial, right? This is at time t at the entrance point as per gas law, and this definition of molar flow rate, molar concentration is molar flow rate divided by volumetric flow rate, Ft upon nu, right? So we can equate concentration based on molar flow rate and volumetric flow rate with the one that you get using gas law equation. So we equate this and this, right? And we get these two expressions at any time t and initially, right, at initial point. So from this you will get an expression that relates volumetric flow rate or volume at time t with the initial volume, right, as per this equation. Now what you will do is, you have concentration, we need concentration in terms of conversion. So we have formula for concentration as Cj is equal, for any species j, Fj upon nu. So for nu we will substitute this here, this way, right? So what you get is, if you further solve this, this is what you will get, right? Because if you bring Ft above, Ft upon nu 0 is your Ct0, right? And this is the relation between concentration and your pressure and temperature, right? Now we know that relation between Ft and X